So, welcome to problem solving session for Introduction to Group Theory course. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from this course's week 1, that is problems related to definition of groups, examples of groups, symmetric groups, and how subgroups work. Okay, so let us start with first question. And if there is something like if you have any doubt or anything, please stop me and ask me, or you can also, if you don't want to unmute yourself, you can also share your doubts in the chat. Okay, so first question is, we have to check which of the following set G with the given operation star form a group. Okay, so first is G is equal to Z, set of integers. Okay, so let me write this set of integers. And here A star B is defined as A minus B. Second group is G is equal to Z minus 0. Set is set of integers minus 0. And here my A star B is defined as A into B, the normal multiplication which we have in integers. Third is G is equal to this A by B, such that A belongs to Z, B belongs to 2Z minus 0, and GCD of A comma B is 1. This is my G, and how A star B is defined? It is, okay, so A star B here will be A by B star sum C by D, right? Because the elements here are of the form A by B. So this we are defining as AD plus BC by B into D. And the normal addition which we have for rational numbers. And finally, G is just this singleton 0, and this 0 star 0 is defined as 0. So we have to check which of these form group under this operation star. Okay, so any guesses? I hope you all know the definition of group. Oh, someone said that there is an echo. I hope now there is no echo in the voice, right? Please let me know if you can't see or hear me. Other than that, any inputs, like whether any guesses which of the following will be group or not? So let me just give you a rough definition for the group. So we say G is a group under the operation star or dot. Let me write star since we are dealing with star here. If it satisfies a certain condition, so if first condition is that for all A comma B in G we have option A is not a group, true. Okay, we will see one by one. So A such that A star B must be in G. Okay, so when we say group, this operation star is from G cross G to G. Okay, so this map must be well defined. So when I take two elements from G and apply this star operation here, A star B, it must land here. Okay, this A star B. So this is my first condition. Second condition is that for all A, B, C in G, I must have this associativity. So this is kind of binary operation, that is the operation is closed in the group. Okay, and the next condition is associativity. It is called associativity, such that A star B star C must be equal to A star B star C. So it is like when I have series of operations operating first any, like here we have three elements operating any two, first the resultant element will be equal. That's what it means. So first applying star to B and C, then applying whatever the resultant, suppose if it is D, then applying A on D will be similar to applying first A star C, A star B, and if this is some E, then this E star C must be equal to this A star D, which we have here. Oh, I hope this is clear. And the final, not final, and also there exists some element E in G such that for all A in G, this A star E, E star A must be equal to A. And fourth condition is that for all A in G, there exists some B in G such that this A star B is E and this is equal to this B star A. Okay. So this is the conditions which a group must satisfy. So as someone suggested, this first option is not a group. So which of the condition is not satisfied by this group A? So first one is my G is Z and A star B is A minus B. So which condition is not satisfied? So first condition is satisfied in this case. That is subtraction of any two integer is again an integer. And but does this satisfy the associativity? So for example, first condition is satisfied. So let us check for the second one, that if I take A star B star C, then what it will be? It will be A minus B star C. So it is A minus B minus C, right? And but if I take this one, A star B star C, then this is A star, this B minus C. But when I apply this here, this becomes, so this is A minus B minus C, but here it is A minus B plus C. And these two are definitely not equal when I take C to be non-zero. Okay, so for example, if I take A is equal to B is equal to C is equal to 1, then in that case, this A star B star C is minus 1 and this A star B star C is 1, but these are not equal. Okay, you can check this. I mean, what to check? I mean, it's here. 1 minus 1 plus 1 will be 1 here. And this 1 minus 1 minus 1 will be minus 1 here. So this first option is definitely not a group. Okay, so second one, Z minus 0 but with multiplication. Any guesses for this? Which condition associativity is not B is not a group? Again, B is not a group, correct like guess by Om Prakash. So G is Z minus 0 and A star B is my AB, and which condition is not satisfied? So again here, first condition is clear, right? Because my A and B are non-negative integers, so their multiplication, my A and B are non-zero integers, so their multiplication will again be a non-zero integer. Okay, so that is not a problem here. So first condition about the closeness of this this star operation is there. Now the second one is associativity. But again, we are in integers, so this A star B star C is A star B into C, which is anyway A star B into C, which is ABC. That is okay. And A star B star C is this AB star C, which is ABC. And this is, so these two are equal. The associativity is satisfied. Okay, exactly. So, as again suggested by or guessed by Om Prakash, the existence of inverse is a problem here because see, identity will be there because this is z minus 0, 1 is there. So 1 belongs to z minus 0 is such that this a into 1 is equal to a is equal to 1 into a for all a in this z minus 0. Okay, so multiplicative identity or identity for the group is available in this case. But again, for inverse, there is a problem. For example, if I take a to be 1 in this z minus 0, then 1 star 1 is 1 into 1, which is 1. That is okay, it has inverse. If I take a is equal to minus 1, then again this minus 1 star minus 1 is minus 1 into minus 1, which is 1. So minus 1 has inverse, which is itself. Similarly, 1 has inverse. But if I take anything, for example, if I take a to be 2, then if then 2 does not have inverse. Okay, so for a is equal to 2, there does not exist any b in z minus 0 such that a into 2 is 1. Okay, so for to understand this, the easiest way is 2 into a will be an even integer. But however, on the right hand side, we have 1 which is odd. So it doesn't matter what we take here. So, sorry, 2 into b. So doesn't matter what b we choose here from z minus 0. This 2 into b can never be equal to 1 since LHS is even and RHS is odd, even for all b in z. Is this clear? So this group, this is again not a group. I mean, for most of you, this will be very basic. But there are also few people who are seeing this for the first time. So that's why we are starting from the basics, and we don't want to skip any step to understand what is happening and to understand the definition of group properly. So let us go to the C part, that is this group. This G is A minus B such that A belongs to Z, B belongs to 2Z minus 0. And one more condition is that GCD of A and B must be 1. Okay. And union 0, that is okay. Okay, and this A star B, sorry, A by B star C by D is defined as AD plus BC divided by BD. Okay, and we have to check whether this is group. Yeah, yes. Yes means you think this is a group. Is that a yes? Or I don't know what that yes is for. So yeah, so first condition which we want to check option C is not a group. Yes, option C is not a group. What is the condition which is not satisfying in this case? Like, which condition is closure is not satisfied? Oh, true. So closure is not satisfied here because if I take this element, see, 1 by 2, which is there in G, right? Clearly, B is 2, A is 1. But if I take 1 by 2 star 1 by 2, this will be what? My 2 plus 2 by 4, right? I'm just doing exactly what they have done. So let me write it. This is 1 into 2 plus 1 into 2 by 2 into 2, which is 2 plus 2 by 4, which is 1, right? And this is not there in this G because if I tried this as 4 by 4 to have the denominator to be even integer. So B I want to be from 2z by 0. Okay. So this, if I, or if I reduce this to 2 by 2, then this 2 is in 2z minus 0. But I also want this GCD of A comma B to be 1, which is not true in this case, right? Because GCD of 2 comma 2 is 2. So, I mean, these two conditions are not getting satisfied simultaneously for this 1 by 2 star 1 by 2. Okay, any doubt here? Like how this is not happening? We want denominator to be even always. So the moment and GCD of A comma B to be 1. So if I choose this numerator such that they add up to even integer, and so for example, if I take any, for example, any A by 2 star A by 2 such that A is odd, suppose, then this will be 2A by 2. And just to have the GCD to be 1, I have to cancel them and the denominator won't survive anymore. Because and I want denominator to be some element from 2z. Okay, so that's why this is not a group. This does not satisfy even the closure property for the group. Okay, so operation is not closed. The addition or the star, when I apply star to two elements, it does not land in my group G, not group G, the set G, which I have chosen here. Okay, so I hope this much is okay. Okay, so let's move to the last. So therefore, this is again not a group. C is not a group again. Now let us check for the last one, which is just G is a 0 and my star is 0 star 0 is 0. Okay. And now the closure property. So 0 star 0, 0 is the only element. So I have to check the closure property only on this element 0. So this 0 star 0 anyway belongs to this set 0. Okay, let me just write this 0 and this belong here. So first property is satisfied. Second, associativity, we only have this one element. So it is 0 star 0, which is 0. I mean 0 star, which is again, this is 0 star this 0. Let me write the bracket to understand which one is which. And this is anyway 0. So second condition is satisfied. 0 is the only element here. Or O, I mean, this could be anything. And you just take any A, G to be any A. The symbol doesn't matter in this case. Just any, I can just put maybe dot here. Very bad notation, but any element here, this star. doesn't matter. This singleton such that singleton set with this operation, we are checking whether it's a group or not. Third one is my identity. So 0 itself can work as a identity here. So because 0 star 0 is, let me call this 0 for now. And so this 0 works as a identity here for this set, and 0 again also works as inverse of itself here. So it satisfies all the conditions, the only element in the group, and such that the multiplication is this, is defined like 0 into 0 is 0. So this forms a group. So this is the only group which we have so far. So let me write here. So G is grouped with this star because this is the only. So out of these four, only this one is the group. The any doubts here? So first one did not satisfy the associativity. This one does not satisfy the inverse property. And the last one was not even the third one did not even satisfy the closure property for the group. Okay, so yeah, I hope this much is clear. If you have any doubt, please let me know. Otherwise, we will move to the next question. Is this clear? Please let me know if there is any doubt. Otherwise, I will move to next question. So let G be a group such that for all A in G, my A square is 1. Okay. So A square is 1 when I'm writing A square is 1. This 1 is my identity in a group. Okay. Let me write here where 1 is identity of group G. Then my option that G is always abelian. B part is that G is finite. G is infinite. And D that G has only two elements. So we have to check these conditions, not the conditions. We have to check which of these holds for this question. So G is such that A square is 1. So A square, so A applied to A under the group application, group operation. This A square is 1. And we have to check whether G is always abelian or not, G is always finite, G is always infinite, or G has only two elements when G satisfies this property A square is equal to 1. So any guesses for this?
Excuse me, ma'am.
Yes.
In the previous question, you have been saying that C is not closed. Can you explain it again? How is it not closed?
So which one? This?
Yeah.
This. So we
Yes,
want
ma'am.
B to be, so when I am writing A by B here, so I want this to be of the form sum 2C, where C is non-zero integer. And GCD of this A comma 2C, I want it to be 1. And here when I get this 4 by 4, and I want GCD of So if I am write this 4 by 4 here or 2 by 2 here, so this is my A by A, and GCD of A by A is, I mean 4 by 4 is 4 here, which is not equal to 1, the second condition which must satisfy. And if I remove, if I make this GCD 1 1 for numerator and denominator, if I make them to be 1 1, then this second condition is not satisfied. So if this is my A by B, so B belongs to 2Z minus 0 is not satisfied in this case. Is this okay?
Okay, ma'am. Thank you.
Yeah. So these two conditions, we have to check how the G is defined. G is such that it always wants B to be inside 2Z minus 0, and a GCD of A and B must be is equal to 1. Satisfying these two simultaneously is the problem for this 1 by 2, 1 by 2 case. Okay. Yeah. So question 2. Any suggestion, any guesses? A square is equal to 1. Any, so see, if we whatever we say, we have to either prove it or we have to give the counter example. Okay, so as Amit suggested that option A is true. Okay, so we have to prove it. So how to prove? Can someone suggest? Anyone has any suggestion? So G is abelian. So let me tell you what is abelian means. Definition. G, comma, dot is said to be an abelian group if for all A, comma, B in G, I must have this A dot B is equal to B dot A. Okay, this is what abelian means. Okay, if anyone does not know what it means, the abelian means the operation must satisfy the commutativity. AB must be equal to BA. This does not happen in general in any, does not happen in general for the groups. Okay, so we have to prove that G is always abelian. We are given that. So if I want to prove that AB is equal to BA, I have to start with AB. So we have to prove this A. So let A comma B be in G. Okay, so once I have A comma B in G, it implies that A square is 1 and B square is 1, right? Because A and B are elements of G. Now let AB, now, so G is group, so AB belongs to G. So this imply that AB square is also 1. This much is clear so far. A and B is in G, so A square and B square is 1. And since A and B are in G, so A dot B will also be in my group G. So since A dot B is in my group G, their square is equal will be equal to 1. Okay, and so what does this imply? That, just a second. So let me. So since AB square is 1, this imply that AB into AB is 1. This implies what? That AB inverse is AB, right? Any doubts here? AB inverse is AB into AB because this AB into AB is 1. So AB inverse is A into B. But in general, this AB inverse is what? It is B inverse A inverse, right? But since A square and B square are 1, so these imply that A inverse is A and B inverse is B. So B inverse is B and A inverse is A. So I got this, my BA is equal to AB. This is equal. So therefore my G is abelian. Because I started with any A and B in G and I got that AB square. Sorry, AB is equal to BA. Is this okay? This you know, right? This AB inverse is B inverse A inverse. Because see, what this will be because of, sorry, AB inverse means AB into this is AB, B inverse A inverse, and this is AA inverse. So it is 1. So this is always there. This I hope you know. Not this is easy verification, you can do this. Any doubts here, like how we proved that G is abelian? If you have any doubt, please let me know. Now, so the first one is true. Now let us check whether second one is true or not. G is finite. So they say, so A square is equal to 1. So do you have any, so will this always be finite if this condition is happening? I mean, this is happening in group G, that A square is 1. A square is 1 means when I'm writing A square is equal to 1 means I'm considering this. Okay, so the operation here is multiplication. And when I say A square is equal to 1, it means the identity is my 1. And if I am writing this G under group addition, then it means that A plus A is equal to 0. Just the notation. The point it makes is that when I apply group operation on a same element, so like A applying operated on A, or A not operated is not the right word, but if I take A into A or A plus A in the group, the element is the identity element. That is what this condition signifies here. So if my group is with respect to multiplication, I can write it as A square to be 1. On if it's with respect to addition, I will write A plus A to be 0. This 1 here is just representing the identity of my group. So do you have any example, or it's always the case that if this condition is satisfying, that A square is 1, then my group G is always finite? Is this true always? Or can you give me some example or counter example or anything? Or any cases or no guess? So this condition is not, I mean, this statement that if A square is equal to 1, then G is finite is not true. Because we can take this. Okay, so let G is equal to Z2X with respect to addition. Okay, I hope you know what Z2X is. So Z2 is just this 0 bar comma 1 bar. Okay, and Z2X are polynomials such that coefficients are coming from Z2. Okay, and so if I take any A in Z2X, then A plus A will be this 2A. And once I have 2A, it becomes 0 in Z2 bar. Sorry, Z2X. Is this understandable? If not, so let me take this. Let FA is equal to A naught plus A1X. These are all plus A2X square and so on. AK x power K in Z2X. Then what is A plus A? This is this, right? 2A bar plus 2A1 bar x, so on up to 2AK bar x power K. And in Z2X, this is 0, right? This is 0 bar plus 0 bar x plus so on 0 bar x power K. And this is nothing but 0. And this is infinite. This is always infinite. Not always infinite. I mean, this G, this cardinality of G is infinite because this 1 bar x power K belongs to Z2X for all K in Z. Okay, and they are all distinct. That x power, I mean, for each power, they are all different. Is this okay? So G need not be finite in general. So this statement is not true. So this is the example where G was infinite. So will G always be infinite if it satisfies A square is equal to 1? This must be, this is N. We have to, so here therefore G need not be finite. Okay, so if so the example which we saw here, the G was infinite. So will G always be infinite if this satisfies the condition A square is equal to 1? Any guesses or anything? For the fourth option, that G has only 2 elements is anyway false because we have a group where it had infinitely many elements. So this one is anyway gone. So G is infinite. So will G be always infinite in this case? Do you have any example of a group where this condition is satisfied but G is finite? Or can we prove that it is always infinite? Any guesses? So this is not true, right? Because we know this. Yeah, exactly. K for group. So K for group is consisting of only 4 elements, A, B, C, and all of them are such that A square is equal to B square is equal to C square is equal to E. Again, this E is my identity. And we have this AB is equal to C. And the moment I have AB is equal to C, all the other conditions are satisfied, that AC is equal to B, BC is equal to A, and so on. Okay, and this is a group which satisfies that all A square, B square, C square is E, and the group has only 4 elements. So this is finite group such that let me write it, x square is equal to 1 for all x in G, but G is not infinite. So we one means this identity. Well, let me write E. Okay, so we got that a square is equal to 1. If that happens, then G is always abelian, but we can't talk anything about the cardinality of G. G could be finite, G could be infinite, and G definitely does not have only two elements. We saw a group which satisfies this condition has infinitely many elements. We saw a group which has finite elements and it satisfies a square is equal to 1. But the moment I have a square is equal to 1, I will always have that G is abelian. Option B. So option B, that G's cardinality of G is infinite, that one, right? So this set is infinite. This is clear, right? This Z2X is infinite set, right? This much is clear because this x power k belongs to Z2X for all k in Z, sorry, k. All the powers of x power k are there. And none of them is equal. I mean, this x power k is not equal to x power j for all k not equal to j. Okay, the powers are distinct. All of them are distinct. So this is infinite set. So this, if I take x power k, k belongs to n, this belongs to Z2X. And how this x square is equal to 1? Understand that we are not multiplying the polynomials. We are adding them. I am considering this Z2X under addition. So when I have to check that a square is equal to 1, here, since this is addition, I have to check that whether a plus a is 0 or not. This a square means this is a dot a is 1. This is my group operation and this is my group identity, right? Identity. And in Z2X, comma plus, group operation is addition and group identity is 0. So when I have to check this a square is equal to 1 in this group G, I have to check that a plus a is equal to 0 bar or not. That 0 is the identity of my group. Is this okay? So when I am taking any f or any element, so element here are polynomials with coefficients from Z2. So any element here in Z2X is of this form, right? A0 x, A0 plus A1x plus A2x square, so on, plus AK x power k, where, let me not write these bars here, where this AI belongs to x power k, right? Sorry, Z2. So this is either 0 bar or 1 bar. So for example, one example here is 1 bar plus 0 bar x plus 1 bar x square plus 1 bar x cube. Okay, this polynomial is in Z2X. And this is just an example, okay? And when I add this, if I take this, my f to be this, then f plus f will be what? 1 bar plus 1 bar. And again, like polynomials, I will be adding the component wise, the powers together. 1 bar plus 1 bar x square plus 1 bar plus 1 bar x cube. And this 1 bar plus 1 bar is 0 bar, which is 0 in my z2. So this is 0 bar plus 0 bar x bar plus 0 bar x square. Again, this is anyway 0, so it doesn't matter. And here, this is 0 bar x cube. So this is nothing but 0 bar, which is my identity of group. Is this okay? And this is my group operation. So it is really necessary to understand what this means, okay? A square is equal to 1. The square here is just the operation, the way they have written it, okay? Understand this part, that what it actually means, okay? Any doubts here? If not, we can then move ahead. This is P again explained. And now question 3, I guess. Question 3 is the if you have any doubt, please ask, okay? In the chat or unmute yourself. Otherwise, I will move to next question. The order of the permutation 2, 3, 1, 5, 4, 6 in S6 written in one line notation is. Someone asked in the discussion forum what this one line notation means. I will explain this, okay? So the option is 2, B option is 4, 6, and D option is 8. I hope you know what order of a element in a group is. Right? So order is, so for A in G, let me write operation to be this. The order of element A is the least positive integer, positive or non-negative. Actually positive integer such that A integer, say positive integer, n such that A power n is 1. Again, this A power n means we are operating A n times. We are multiplying A 1 times, or we are adding A 1 time n times, depending on the operation of the group. And this one is just identity. So just like if my have group is H comma plus, then this becomes that A plus A n times. When we add A n times, then it becomes 0 of the group. Okay, and if there is no, there does not exist any n such that, what I can say, that A power 1 is 1, then we say that order of A is 0. Okay, so if there exists some integer, some number such that A power n is 1, then we say that and we denote it like order of A is n, order of A is 0 in this case. Okay, if there exists n such that A power n or adding A n times give me the identity of the group, then the order becomes n and it has to be least positive integer or 0. Okay, why least is because otherwise it won't have any significance, because if A power n is 1, then A power 2n will be A power n into A power n, and this is 1 into 1, which will be 1 anyway. So we say that order is the least positive, the smallest number such that this holds, A power n is equal to 1. Okay, and here we have to find the order of permutation. So I hope you all know what is permutation group is, right? It is set of all permutations. So what can I say? It is of this form 3, 4, 5, 6. This is not very good way to write. Sigma I1, sigma I2, not even I, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, such that sigma is bijection from set 1 to okay, this is one of the way writing this permutation group. And what this cycle 2, 3, I think 5, 1, 5, 4, 6 means, it means this 1, 2, 3, 4, 5, 6, and this means 2 is going to 3. So 2 is mapped to 3, 3 is mapped to 1, 1 is mapped to 5, 5 is mapped to 4, 4 is mapped to 6, and 6 is mapped to 2. Okay, so this is what one line representation of a permutation means. It is just the way of writing them in terms of cycles. Okay, and we have to, and how the multiplication works here is like this. If I have, let me write this form here 1, 2, 3, 4, 5, 6, and here 5, 3, 1, 6, 4, 2, and I have to apply multiplication here. So how it works? It is again some permutation here. So how it goes? 1 goes to 5, and here I check 5 goes to 4. 2 goes to 3. We start from right and go towards left. 2 goes to 3, 3 goes to 1. I hope that's where it is going. Now 3 goes to 1, 1 goes to 5, 4 goes to 6, 6 goes to 2, 5 goes to 4, 4 goes to 6, 6 goes to 2, 2 goes to 3. Okay, so this is, if I call this cycle, let me call this element A. So A square is this, which is not yet an identity element. Okay, and A cube will be just this element multiplied by again my cycle. So we have to check how, I mean, the multiplication is clear, right? How the multiplication is defined here and what this cycle representation means. If not, please let me know. And 1, 2, 3, 4, 5, 6. Here 4, 1, 5, 2, 6, 3. And 1, 2, 3, 4, 5, 6, 5, 3, 1, 6, 4, 2. And what this gives me 1, 2, 3, 4, 5, 6. I hope what I'm doing is I'm not missing on anything. 1 goes to 5, 5 goes to 6, 2 goes to 3, 3 goes to 5, 3 goes to 1 goes to 4, 4 goes to 6, 6 goes to 3, 3 goes, sorry, 5 goes to 4, 4 goes to 2, 6 goes to 2, 2 goes to 1. As long as I am getting distinct numbers in the bottom, I am okay. Okay. Otherwise, there is some problem because this is bijection, right? So, two elements should not go to one number from top to bottom. So it's like when I'm writing this, it is actually the bijection such that, and if I want to write bijection from here to here, my 1 is going to 6, 2 is going to 5, 3 is going to 4, 4 is going to 3, 5 is going to 2, 6 is going to 1. Something like this is happening. Okay, that's what permutation means. So this is just function. And when I apply this multiple times, so it is like I'm composing a bijective function. And composition of bijective function will still be a bijective function. Okay, so when I am doing this, when I apply this 2 times, so it is like my, what is image of 1? Image of 1 is 6 here. Okay, and okay, so this is the bijection which we have. No, sorry. Let me write this one. 1, 2, 3, 4, 5, 6, and here it is 1, 2, 3, 4, 5, 6. 1 is going to 5, 2 is going to 3, 3 is going to 1, 2 is going 2 is going to 3, 3 is going to 1, 4 is going to 6, 5 going to 4, and 6 going to 2. So when I apply this twice, so 1 is going to my 5, and here 5 is going to 4. So that's what is happening here. 5 is going to 4. And again, so composition of functions, please understand it that way. It's easier to understand that way. And then it you can understand what this a square and this a cube means. And here also we can easily see that when I take square of this a cube square, that is apply this cycle twice, or multiply this cycle, I will get identity, because here see 1 goes to 6 and here 6 goes to 1, 2 goes to 5, 5 goes to 2, 3 goes to 4, 4 goes to 3, and that is happening. So clearly from here, a cube will give me this, sorry, a power 6 will give me identity. That's there. But again, we want to check for the least element. So from here, we can clearly see that this is happening. This is my identity function, which I get here. But I want to check whether this is least. So I need to check whether a power 4 gives me identity or not. I mean, identity permutation or not, or a power 5 whether gives me identity permutation or not. Okay, so that's why we need to check what happens here. These are only two. And 5, 3, 1, 6, 4, 2. 1 goes to 5, goes to 2, 2 goes to 3, goes to 4, 3 goes to 1, 1 goes to 6, 4 goes to 6, 6 goes to 1, 5 goes to 4, 4 goes to 3, and 6 goes to 2, 2 goes to 5. Okay, and the final check 2, 4, 6, 1, 3, 5. This 1, 2, 3, 4, 5, 6, 5, 3, 1, 6, 4, 2. And the final one which I need to check 1, 2, 3, 4, 5, 6. 1 goes to 5 goes to 3 to, I mean, I know this. 4 goes to 6 goes to 1. Wait, 4 goes to 6, 6 goes to 5, 5 goes to 4, 4 goes to 1, 6 goes to 2, 2 goes to. Am I making some mistake here? Did I miss something? 2 goes to 3, 3 goes to 6, 3 goes to 1, 1 goes to 2. Yeah, now this is correct. And a power 6 will be anyway equal to this because of associativity which we have. So that's not a problem. So when I am writing this, so a power 6 will be a power 5 into my a, but I can do this, right? Because of associativity, I can do this into this, which is a cube into a cube, and which we saw is equal to identity. You can check this. Write this and try to multiply this and take this a cube square. It will be the identity permutation. So, and no integer lesser than 6 is giving me a power k is equal to identity for k less than 6. So my order of this group is definitely 6. Okay, it's not 2, it's not 4. It's definitely not 8 because 6, no, how do you wrote one notation in long form? So from cycle to the form, so for example, if I have this cycle, 7, not 7, let me keep. Let me also write, okay, date 5, 4, 3, 2, 1. If I have this, it means my permutation is anyway from here to here. But when I have this cycle form, the cycle says 5 is going to 4. So here 5 is going to 4. 4 is going to 3. 3 is going to 2. 2 is going to 1. And 1 is going to 5. This is my cycle. This is very bad example, but if I take also this 2, 3, 5, 4, 1, look at this as a cycle where what is happening. So it is like arranging this number in cycle 2, 3, 5, 4, 1. So 2 is going to 3, 3 is going to 5, 5 is going to 4, 4 is going to 1, 1 is going to 2. What does this mean in this long form? Where does my 1 goes here? To 2. Where my 2 goes here? 3. 3 goes to 5. 4 goes to 1. 5 goes to 4. Is this okay? And from here also we can write cycle form, right? Take any permutation, write whatever you want. What is missing now? 5. So here 1 is going to 2, 2 is going to 3, 3, sorry. Yeah, 1 is going to 2, 2 is going to 3, 3 is going to 4, and 5 is as it is. So it doesn't matter where it goes. Or let me write this in better form. 5, 2, 3, 4, 1. So 1 is going to 5, where my 5 goes to 4, 4 going to 1 again, and 2 and 3 are as it is. So this doesn't matter. So 2 is going to 2, 3 is going to 2. We either write it or we don't write it, doesn't matter. It won't make any change. But that's how cycle are written. So cycle to long form to cycle. I hope this is clear now. Okay. Anyone else? I mean, I hope this is clear because someone also raised this question about what this long form or cycle notation means. Okay, so this is what it means. And yes. Uh, so order of this cycle was 6. Okay, so the question here, I hope we corrected this. This is next question. This question now, again, it is related to which question number is this? 4. Question 4. Let me just. The inverse of 2 bar in Z mod 7Z comma plus is, this is easy question, but I'm writing this just to clarify the difference between addition C and D 7 bar. So inverse of 2 bar in Z mod 7Z plus. So Z mod 7Z plus operation is, group operation is addition and identity is 0. Okay. So I want to find element x such that x plus 2 bar is 0 bar in Z7. So what that element will be? Any suggestion? I mean, any guesses? I mean, clearly, right? 1 bar plus 2 bar is 3 bar, which is not equal to 0 bar. 3 bar plus 2 bar is 5 bar again, which is not equal to 0 bar. 5 bar plus 2 bar is 7 bar, which is 0 bar, and 7 bar plus, exactly. 7 bar plus 2 bar is 9 bar. But 9 bar is what? It is again 2 bar. And anyway, this 7 bar is anyway 0 bar in Z mod 7Z. So the only correct answer is this. And understand that the inverse in a group is unique. So if 5 bar is inverse of 2 bar, then 5 bar is the only inverse of 2 bar. So in exam, if you are writing exam for the course, if you see that some element, if you are asked to find inverse, if you find one element, that is enough. You don't have to. Even in MSQ, they might ask to find inverse. I mean, whatever kind of question. Once you have inverse for some element, that's the only inverse it has. Inverse is always unique in a group. Okay. And next is, yeah, next question. We'll try to solve. Yeah, this one. Question, I guess this is question 5. Consider the subgroup MZ and NZ of the group Z. Okay, and then which of the following statements are true? Okay, so and here we assume that M and N are non-zero for convenience. So they are saying that MZ is contained in NZ if and only if M divides N. Second, MZ is contained in NZ if and only if N divides M. Third one is that LCM of M comma N belongs to this MZ plus NZ. And fourth one is MZ plus intersection NZ is non-zero. Okay, so this is the question. And I hope you all know what subgroup is, right? So definition or just recall that if G comma dot is a group, then H, a subset of G, is a subgroup of G if H is a group H comma this dot which is same as here is a group of group under the same operation. Okay, so this same operation is really important. Then only we can say that this is group. Okay, for example, if I take Z7 under addition and take this Z7 minus 0 under multiplication, these two are group and this Z7 minus 0 is contained in Z7. But these two are not related as, I mean, they are not subgroups of each other. I mean, definitely this is under addition, this is under multiplication. So this is subset of Z7 over which we have some operation and we form a group out of it. But this itself is a group, some H, but this is definitely not subgroup of my original group G under addition. Please understand this. Okay, here the multiplicative, the identity of group is 0. Here the identity of group is 1. Okay, so it's important to understand how the subgroups and everything work, especially when we are working in such groups where we know we can define multiple types of operation and form group out of it. Okay. So when we say that H is a subgroup of G, it is subset of G, okay, but it has to have the same operation as my G, and the identity coincides with the identity of G. Identity of H is exactly equal to the identity of G. Is this okay? The understanding of subgroup and how the operation inherits to H from G. So again, first is we have to check what they are saying is that this mz is contained in nz if and only if m divides n, I think. Is this true? First of all, for this example, when I'm saying this mz is contained in mz, note that what this m is. It is, this mz is just m into a such that a belongs to z. So it is multiples of m in z. Okay, and the moment I say that m belongs to nz, note that this entire mz will belong to nz, because nz is what? Nz is a group. So it, if some element m is in nz, then m plus m will be in nz, right? And this implies this m plus m, some k times, will be in nz. And the moment I have m in nz, this minus m will be in nz and all the powers of its inverses and so on. And 0 will definitely is there in nz. So when I'm saying that this mz belongs to nz, it's enough to check whether this element m belongs to nz or not. because the moment I have M inside this NZ, the entire MZ goes inside my NZ. Is that okay? If not, please ask. Understand that to check whether this entire MZ belongs to NZ or not, it is enough to check whether M belongs to NZ or not. That's the only thing which I'm pointing out here. So we have to check MZ belongs to NZ if and only if M divides NZ or not. So if I have MZ belongs to NZ, this implies that M is this implies that M belongs to NZ, right? Because M into 1 belongs to NZ. M is equal. So this imply that M is equal to some N into B or some B in Z. So these imply that then from here I can't conclude whether we can't conclude whether M divides, sorry, yeah, M divides N or not. Okay, and just because I have M dividing N, can we say that MZ contained in NZ? Can you give me some example of M dividing N? So for example, my 2 divides 4, right? But is 2Z contained in 4Z? Here the elements of this form 2 into A such that A belongs to Z. Here the elements are the form 4 into B such that B belongs to Z. This is definitely not contained here, right? Because 2 belongs to 2Z, but 2 definitely does not belong to 4Z. So this condition is not satisfied. Okay, so this MZ contained in NZ, if and only if M divides N, is actually false. Okay, any doubts here? And also to check the other condition, if I take N is equal to 1 and M to be any integer not equal to 1, then this MZ is contained in Z, right? 1Z, which is my Z, but definitely M does not divide 1, right? Only 1 divides 1. And I can take this Mn to be just greater than 0 maybe. Anyway, Mz and minus Mz are equal. You can check this. So this is also one way to understand that this condition is not true. Okay, even this condition also fails. Okay, now second condition, which they are saying that Mz contained in Nz if and only if N divides M. Okay, so it's all, so first condition that Mz is inside Nz. This imply what? That M in particular belongs to Nz, and this implies that M is equal to some N times B where B belongs to Z. So this imply definitely my N divides M. From here we can say that this is the condition which we got. So this is easy, that if Mz contained in Nz, then N definitely divides Mz. but it's other way around true. So what they have given is that n divides m. And to show that mz is contained in nz. And again, as I said earlier, it is enough to show that, okay, enough to show that m belongs to nz, as m belongs to nz implies that entire mz belongs to nz, because this is subgroup of z and it is subgroup of z, it means it is a group itself and it is closed under addition and multiplication and so on. Not multiplication, it is closed under addition, has identity and has multiplicative inverse and so on. So this is there. So it is enough to show that m belongs to nz. Are you with me for this? That it is enough for me to show that m belongs to nz. Okay, so n divides m. This implies that m is equal to some n times b, where b is some integer. So this implies that m anyway belongs to nz, because this nb belongs to nz. So therefore m belongs to nz. So yeah. So therefore mz is contained in nz. Any doubts here? From here to here, I can go without any problem. Please let me know if this is not clear. So this implies that mz is contained in nz. Is this okay? Please let me know if not. Otherwise, I will move to next. The next they are saying is LCM of m comma n belongs to mz plus nz. Is this true? First of all, is this true? Or do you have any example where this does not hold? Okay. You know this formula for LCM, right? It is m into n divided by GCD m comma n. Okay, and the moment I have this, I can write this, right? N divided by GCD m comma n. GCD m comma n definitely divides n, so this is some integer. Okay, so this is what? This belongs to mz. Okay, and the moment if it belongs to mz, so this belongs to m, this mz is contained in nz plus nz. So, and I hope you know what this is. This is am plus bn such that a comma b belongs to z. Okay, for this group. And in general, so this is for addition, and if and in general, this if h1 and h2 are a group, so this is just ab such that a belongs to b, sorry, a belongs to h1, b belongs to h2. And when I'm writing this am plus bn, this actually means that this am belongs to mz, bn belongs to nz. Okay, so this is just, and this everything is happening inside my original group G. Here, this is happening inside my Z, and this is happening, this H1, H2 is happening inside my G dot. Let me just write this. Is this okay? So this belongs to mz and mz is contained in mz plus nz. Because see, mz is what? M into A. I can always write this as 0 into B, which belongs to mz plus nz, right? 0 belongs to nz. So this is there. Okay. Any doubts here? So LCM of M and N will always be an element in mz plus nz. Please let me know if you can't follow anything. The last one is mz intersection nz is 0. Is not 0 is the question, right? So for now we have this one as true. We proved this. We got this. And the last statement, mz intersection nz is non-zero. So can we always have this, that mz intersection nz is non-zero? Note that we proved the second statement, that is mz contained in nz. Let me just change the numbers. Pz contained in qz if q divides p, right? So anyway, this m will always divide mn, right? So this will imply that this mnz is contained in mz. Similarly, from part 2 of this question, similarly n divides mz. So this mnz is contained in nz. And then we have this. So from these two, if mz is in mnz is contained in mz, mnz is also contained in nz. So this mnz is contained in this mz intersection nz, right? Is this correct? Or is there any doubt here? So this mnz is contained in mz intersection nz, and this will be non-zero since mn are non-zero. So m into n is non-zero. Please let me know if this is okay or if you have any doubts. Okay, if not, then so this one is correct. Okay, and if you don't even want to go to MZ and MZ, just simply checking that a element Mn belongs to Mz and element Mn belongs to Nz. Okay, so this implies this element Mn always belongs to Mz intersection Nz. So therefore, and since Mn non-zero, this M into N is non-zero. This implies this Mn is non-zero belongs to Mz intersection Nz. Okay, I hope this much is clear. Okay, if you have any doubt, this element Mn which and now if you have any doubt, please let me know. Otherwise, I will move to next question. I think it is question 6 or 7. 6. The infinite tuple of non-zero real numbers form a group under the component-wise multiplication. So this is the question. We have to check whether this statement is true or false. So they have said that the infinite tuple of non-zero real numbers form a group under component-wise multiplication. Any guesses whether this is true or false or anything? So first of all, since this is real number at each component, so for first the binary element, if my tuple is suppose a1, a2, so on, and if I want this b1, b2, and so on, let this belong to this group infinite tuples from a group. And let me just write this formally. Let G is equal to an so on such that ai belongs to r minus 0, and for a comma b in G, a dot b is a1 an and b1 to bn dot 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 is a1 b1 a2 b2. That's what component wise multiplication means, right? Bn an bn and so on. This is my multiplication defined. So first, at each component, these AIBIs are integers. Sorry, are real numbers, non-zero real numbers. So whenever I multiply them, I will get a non-zero real number at each component. Okay, so if I take for any a comma b belongs to this group G, this a dot b is a1 b1 a2 b2 an bn so on, and each ai bi are non-zero, so ai bj is non-zero, so ai bi will be non-zero. So this will again be an infinite tuple of non-zero in real numbers. So these imply that A, B belongs to G for all I. Okay, I hope this is clear. Each AI and Bj is non-zero, and their multiplication at each component will again be non-zero since AI and Bi are non-zero. So this AB still belongs to G. So therefore the closure is satisfied. Now the second condition about the associativity. So if I take A, B, C in G, then this A, B into C will be A1, B1 into C1. I'm directly writing this A2, B2 into C2 and so on AN, BN, CN and goes. This will be equal to this, right? Because this is what? This is A1, B1, C1. We are in real numbers A2, B2, C2, AN, BN, CN, and now this one is A1, B1, C1, and this is equal to this A2, B2, C2. So this associativity is also satisfied. And now the identity element, the existence of identity. Can someone guess what will be the identity for this group? Let me, so this 1 or E is equal to 1, 1, 1, 1. This is 1 at each component will form the identity of this group because A dot E will be just A1 into 1, A2 into 1, so on, AN into 1. And this will anyway be because we are multiplying in reals. So this is, and this will also be, this is equal and these two are equal. Okay, so this identity exists and it is there, and again the each component of this element E is 1, 1, 1, which is non-zero. So this belongs to my G, my set G. And fourth one is multiplicative inverse. So we are in R. So for each A in G, A is A1 to AN and so on. And for each, not for A in G, A is this, and for each AI non-zero, we have BI non-zero in R such that AI into BI is 1, right? Non-zero real number has inverse. So we said this B is equal to B1, B2, Bn, and so on, where Bi is equal to AI inverse in R multiplication. Okay, and then this by choice of my B, this A1, B1 will be 1, A2, B2 will be 1, and so on. And this will work as inverse for my element A. I hope this is clear. This was just easy cross-checking of whether this forms a group or not. And this is true. Is that okay? If you have any doubt, please let me know if anything is this. Here, note that this significance of R was not of, there was no significance of choosing R with multiplication, component-wise multiplication, and so on. If you have any group G here with multiplication, and if you take this maybe script G to be infinite tuple of elements of G under component-wise multiplication, then also this G, this script G under this component-wise multiplication, this will still form a group. Okay, so this one needs to understand. And not only we have to repeat G, we can take any, suppose Gi comma star could be anything, Gi comma star I is our groups. Then again this, if I take this G or maybe H, such that this is G1, G2, Gn and so on, where Gi belongs to this Gi star I, this will also form a group. Okay, and we have to choose inverses and identity. So it is like identity will be E1, E2, En, and so on. And the inverse will be like that. For example, G1, the first component for this element, the inverse will be G1 inverse, G2 inverse, GK inverse in each group Gi of at the position I. Okay, so this is just example. So in question, whatever question you are given in the tutorial, they are like very specific examples. They are like very specific cases or particular example which is given, and you can definitely uh, try to generalize those, whether this works for any. See, when I say this, I mean G needs to be group, right? This Z under multiplication is not a group itself, right? So that won't work here. When I'm saying this R here, R into R under multiplication, this, sorry, R minus 0 under multiplication is a group. This Z, we just saw, right? This is not group. The group condition is important. Instead of when I said this, instead of R, so for example, forget about the infinite tuple. If I take this Z2 comma plus, sorry, Z comma plus and R minus 0 comma multiplication, and my G is A comma B such that the infiniteness will follow from this. A belongs to Z and B belongs to R minus 0. This is R minus 0. And this A comma B is what? A plus B comma, A comma B, and suppose G is under star. C comma D is A plus C comma B into D. At each component, we need to have a group. That's what I'm saying. At each component, we need a group. Z comma 0, Z minus 0 comma, this is not group. So that's what it won't work. Okay, is this okay? Like what I'm trying to say here? Something at each component, we need to have a group. This will form a group. You can check. Okay, here identity will be 0 comma 1. For A comma B, the inverse will be minus A, B inverse. Is this okay? At each component, so this is like, if I call this G1, this G2, so this is G1 cross G2. Each component has its own multiplication and its own operation or its own addition. Is that okay? And each of them is a group. Okay. Yeah. So let us move to next question. This is, I think, question 7. Yeah. Question 7. Find the inverse of the congruence class 3 bar in U5. Okay. We have to find the inverse of congruence class 3 bar in U5. So what is U5? U5 is Z5 minus Z0 under multiplication. Okay, so U5, so Z5 is what we know is 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar, right? And this is group under addition. And this U5 is this Z5. What is bar here? Okay, so this Z5 actually means Z quotiented by 5Z. Okay, and what does this mean? I think the quotients of a group is not yet defined, I guess. I'm not sure. Just let me check whether it's defined or not. Yeah, it's not yet defined, but what it means is if I take, so it is like we go modulo 5. So if I take 3 bar plus 5 bar, so it is 8 bar, but I want to check it in Z5. So it is like we are taking, so two elements. So in Z5, two element, let me write this. Z5 is equal to Z my 5Z. What is 5Z? 5Z is 5 into A such that A belongs to Z, right? And if I take any element A bar in Z5, it is congruence class such that A is related to B if 5 divides A minus B. This is the congruence class. And each of this relation will form, under this equivalence condition, we form congruence classes here. So it is like when I write this 0 bar, so 0 bar in this Z mod 5Z means all these elements. So 0 is related to 5 because 5 minus 0, 5 divides 5 minus 0. 0 is related to 10 because 5 divides 10 minus 0. So this class of 0 bar actually contains all these elements 0, 5, 10, all the multiples of 5 in short. So instead of looking at the entire Z, what we are doing is we are clubbing them under this operation, under this equivalence, that A is related to B if 5 divides A minus B. Similarly, what will come under the equivalence class of 1? I mean, not only this minus 5, minus 10 and so on, all those will also be there. Okay, for example, 1 will be related to 6, right? Because 1 minus 5 divides 1 minus 6. This 1 will also be related to minus 4 because 5 will divide 1 minus minus 4, which is 5. So this 1 bar is collection of all the elements of the form. This 1, 5, 1, 6, 11, so on, 1 minus 4 minus 9, and so on. So this is like 1 plus 5z, right? These are all the elements of the form 1 plus 5z. These are all elements of the form 0 plus 5z. Okay, so that's how. So when I say this 3 bar, I mean, you got the idea what this equivalence class means and what this bar means. So when I write this 1 bar, it actually means it signifies this entire class 1 plus 5z. This is equivalence class under this class under relation such and A related to B and only if 5 divides A minus B. And similarly, Z7 and all other equivalence classes work. So Z7 is again, the equivalence classes are A minus B, 7 divides A minus B, and so on. Is that okay? This is not minus, this is multiplication. Is this okay? The bar? Yeah. So now I hope the bar, what that bar signifies is clear. And sorry, here it won't be 5 bar. 5 bar is anyway 0 bar, right? Because any element, I mean, if something belongs here, I mean, we know that if A is related to B, B is related to A. This is equivalence condition. You can check, and A related to B related to A related to B, B related to C, then A related to C, and so that. So the equivalence class of 0 bar is equivalence class of 5 bar, equivalence class of 10 bar, and so on. Similarly, equivalence class of 1 bar is equal to equivalence class of 6 bar minus 4 bar. I mean, no, we don't prefer to write the negatives when we write in equivalence class, but yeah, this is true. Okay, and this is 11 bar and so on. Similarly, the 2 bar will be what? It will be 7 bar, right? Because 7 minus 2, 5 divides 7 minus 2. So 2 bar, 7 bar, 12 bar, and so on. So I hope you understand what this bar signifies. So now what they are saying is inverse of congruence class 3 bar in U5. U5 works under multiplication. Okay, so U5 is what? U5 is under multiplication. U5 is under multiplication. 1 bar, 2 bar, 3 bar, 4 bar. Okay, and how it is? So 1 bar into 2 bar is 1 into 2 bar. Okay, that's how it works. For example, here 3 bar, I mean, just giving you an idea. 3 bar into 4 bar is what? 3 into 4 whole bar. And what it is? It is 12 bar. And what is 12 bar? 12 bar is 2 bar under 5 bar. Okay, so that's how multiplication is defined. And this is closed because of this equivalence classes. We got this 12 bar here, but what is 12 bar? 12 bar is anyway 2 bar which belongs to this U5, the set to U5. Okay, and we have to find now multiplicative inverse of 3 here. So any guesses what will be the multiplicative inverse of 3 here? So there are only 3 other elements apart from 3. I mean, let us multiply and see what is to find multiplicative inverse of 3 bar in U5. U5 is a group. It has inverse and everything. Okay, you can check that. So let us start with 1 bar. 1 bar into 3 bar is 3 bar, which is not my 1 bar. Multiplicative identity in multiplicative identity in U5 is 1 bar. Okay, it is group under multiplication. Okay, unlike Z5 under 0, the identity of the group is my 0. Here U5 is a subset of Z5 without 0, and the identity of this group under multiplication is 1 bar. So 3 bar into 1 bar is 3 bar, which is not equal to 1 bar. So when I'm saying that I want to find the inverse of 3 bar, I want to find, that is to find B in A in U5 such that A into 3 bar, or it is right, A is 1 bar. That's what I want to find. Now let us 2 bar into 3 bar. What is 2 bar into 3 bar? 2 into 3 whole bar, which is 6 bar. And what is 6 bar? 6 bar is 1. Exactly. 6 bar is 1 bar. Okay. So this gives me identity. So therefore inverse of 3 bar in U5 is 2 or 2 bar. Okay. And also, so the moment I have inverse, it is unique. We already have the information that this is group. If you don't know this, then prove, check this, that this is group. This is group. Please check if you don't know that this is group under multiplication. And the moment I have 2 bar is inverse of 3 bar, 3 bar will also be inverse of 2 bar. 1 bar is inverse of itself. So since now we are anyway doing this, let us check what is inverse of 4 bar. 4 bar, let us check. I mean, this is just to find inverse of 4 bar. So again, 1 bar into 4 bar. 1 bar is my identity. So 1 bar into 4 bar is 4 bar. That is, sorry, that is not my 1 bar. Again, 2 bar into 4 bar is what? 2 bar in 2 into 4 bar, which is 8 bar, which is what? In Z5, it is 3 bar. Again, now 3 bar into 4 bar is 3 into 4 bar, that is 12 bar. Under 5, it is 2 bar. And now 4 into 4 bar, it is 16 bar. Let me write this. 4 into 4 bar, which is 4 into 4 bar, it is 16 bar. And 16 bar is now 1, right? It is 1. So we got the multiplicative inverse of each element. So multiplicative inverse, so 1 inverse is 1 bar inverse is 1 bar, 2 bar inverse is 3 bar, 3 bar inverse is 2 bar, and 4 bar inverse is 4 bar itself. Okay, so this U5 is a group and each element has inverse and so on. So any doubts how things are, or any doubts in general from the lecture or anything? I mean, it's already past 8. Okay. If you have any doubt, please raise the doubts in discussion forum, and we can either address them there in the discussion forum, or I can discuss discuss those doubts during this live session. Okay, and notes and link for this discussion will be available in the problem solving session, which is available in the portal. You can access this. So it will maximum be available by end of today or tomorrow morning. Is this okay? Any doubt here, whatever we discussed? Or any doubt from anywhere from the lecture or anything? Others? No doubts. Okay. Then I think we can stop for now, or if you do not have any doubts. And please submit the assignments and raise your doubts in the discussion forum. And yeah, I think we can stop. Yeah, okay. Thank you.